Okay, so in the previous module, we talked about the solution of simple harmonic oscillators, and we derived the eigenfunction and eigenvalue equation for simple harmonic oscillator. We also talked about how to use those eigenfunction and eigenvalue equations for the determination of kinetic energy, potential energy, and the probability of maxima at the ground state level. So all those things we talked about. The next model system which we are going to talk about in today's module is the rigid rotor. And now rigid rotor is a system where we will not be using the Schrodinger wave equations of Cartesian coordinates. We will use the Schrodinger wave equations in another coordinate system called polar coordinates. So first we will try to understand what is a rigid rotor classically, and then what is the difference between the Cartesian coordinates and the polar coordinates, and how we if we convert this Schrodinger wave equations into a spherical polar coordinates, then what is the form of that equation. Okay, so I start with the rigid rotor. Rigid rotor is a system where two mass is connected by a bond, or two mass is connected by a particular distance r. Capital R is the distance between two masses m1 and m2, and the center of mass I have shown is at this point. Center of mass is here. Okay, and and if it rotates in a plane, then the rotating that, it is simple to the picture tells you that it is simply a rotating diatomic molecule where m1 and m2 are the masses of the two atoms connected by a bond of distance r, shown as capital R. Okay, so this gives you another idea that till now what we have done particle in a one-dimensional box. So one particle is moving on a particular line. Then we talked about particle in a three-dimensional box. There was one particle which is moving in a three-dimensional box. Then we talked about harmonic oscillator. There also the single particle was moving on a harmonic oscillator. So how can we convert these if we go for a one particle system? If we change the problem from one particle system to a two particle system. So if we change this problem to a two particle system, the only thing which you need to do is that you, instead of mass of m1 and m2, you use a reduced mass, and reduced mass is shown as mu. Okay, where mu is equal to m1 into m2 divided by m1 plus m2, that you are aware of these equations. Okay, so the moment this is a rotating diatomic molecule can be converted to a one particle problem, provided the this particle with a reduced mass is moving in a plane in a circular path. Okay, so the same thing which we can do in case of simple harmonic oscillator. If you are talking about the vibration of a chemical bond which is connected by two atoms A and B, then instead of saying that frequency of simple harmonic oscillator is 1 by 2 root under k divided by m, which we have written earlier, now it will be, for a diatomic molecule, it will be 1 by 2 pi root under k divided by mu instead of m, and then you can talk about the vibration of a chemical bond also. That's why when we say vibrational spectroscopy, we always say the frequency is to be equal to 1 by 2 pi root under k divided by mu, not k divided by m. Okay, so this two body problem, rotating rigid diatomic molecule, is now converted to a single body problem with a reduced mass mu. Okay, a classical rigid rotor is like this one. Since center of mass is we have defined in between and we have divided capital R into two components, R1 and R2. So if the center of mass is defined, it means M1 R1 must be equal to M2 R2. So that R is equal to R1 plus R2. Now if it is rotating, then there will be an angular velocity and a linear velocity. The angular velocity is shown as omega, linear velocity is shown as nu, and nu is equal to omega. Nu is equal to omega is equal to nu. I think there is a mistake here. So this will be omega is equal to this is angular velocity. Angular velocity is nu is equal to okay, linear velocity is equal to this one. Okay, So we have this relationship, and if we use these relationships, this relationship, then this relationship, then we can write this as this problem. Then moment of inertia we can calculate as summation of mi ri, and this summation of mi ri will give you I is equal to mu r square. So this is an important relation, that moment of inertia is given as mu is equal to ri square. Then angular momentum L is defined as r into p, and this is equal to p is equal to mass into velocity is equal to omega. Okay, this is I, and r into p is equal to I omega. L is equal to I omega. For rotation, for rotation r is perpendicular to p, so we can write this one, and then again you see how do we get L. L is equal, you get from r1 into p1 plus r2 into p2, and then m1 r1 v1 plus m2 r2 v2 gives you this one, m1 r1 square omega, m2 r2 square omega, and then omega is equal to this one, and this is what? This is summation of mi ri is I, so it is equal to I. So L is equal to I. The two important relation from classical rigid rotor is L is equal to I omega and I is equal to mu r square. So these two are important relationship, which is a classical rigid rotor, and you can think of a classical rigid rotor in terms of this one. Okay. Now if we go for kinetic energy, then kinetic energy is given as 1 by 2 m1 r1 square omega square plus 1 by 2 m2 r2 square omega square, and then we reach kinetic energy is equal to 1 by 2 I omega square, or in terms of angular momentum we write it L square divided by 2I. The moment we talk about the rotating motion, angular momentum comes into picture, and linear momentum you know is mass into velocity, and angular momentum is mass into velocity into radius. Okay. So this angular momentum is always shown as L, and it's very important property, quantum mechanical property, about which we will talk about in details in the future modules. Okay. So a classical rigid rotor is a two particle system which is rotating along a fixed axis in a particular plane separated by a distance r. That's all. That's all you have to remember. And then moment of inertia for this rotation is I is equal to omega r square, and the angular momentum is I omega. These are the important relationship from the classical mechanics. Okay. Now I said you that if we are talking about rotating diatomic molecules, then since it is a rotation, so we will not show this rotation in we cannot show this rotation in Cartesian coordinates. So what we will be doing, we will be converting Cartesian coordinates equation of Schrodinger wave equation into spherical polar coordinates. And what is this coordinate? This coordinate is actually this is your Cartesian coordinate. Z axis is here, y axis is here, and then x axis here. So the plane of the board is actually YZ plane, and the x axis is across the penetrating this plane above the board and below the board. Okay. If you have to say the position of a particle of a particular point in a Cartesian coordinate, you write x1, y1, z1 three coordinates, and you say the position is defined. In case of a spherical polar coordinates, if you have to show the particle is shown in red with p written, then what we do, the first thing which you calculate is the distance from the origin of the particle. Okay, and this distance is shown as r. So r is the first coordinate of spherical polar coordinates. Okay, and position vector, we say r is a position vector, and this is equal to r square is equal to x square plus y square plus z square. The second thing is that if you draw a line from the a projection from the origin to the particle, then whatever the angle this line is making with the z axis is called theta angle, and this is called azimuthal angle, and this is angle between z axis and the position vector. Position, because from the origin we are talking about the particle, distance between the particle and the origin is called r. If you look at this one, the particle could be anywhere in the space. So if you have to draw a line from origin, you can draw anywhere a very big line, or it could. So what does it tell you? It tells you that it could be very close to the origin, it could be very far away from the origin particle, and then we say r could vary from 0 to infinity. It could be anything. Okay. Then we say that after that the second coordinate is theta, because whatever is the line drawn from the origin to the particle, whatever angle this line makes with the z axis is called theta angle. And then what you do, from the point you drop a perpendicular in the xy plane. Xy plane is a plane cutting across the board. Okay, this is how xy plane is going. Okay. So if you have an xy plane and you drop a perpendicular on the xy plane, then this perpendicular, and after dropping that perpendicular, again you draw a line from that point in the xy plane to the origin, and whatever angle this line is making with the x axis is called phi. So phi is the third coordinate. So in a spherical polar coordinates we have three coordinates, r, theta and phi. R is the distance. I hope you understood this, because this is a three-dimensional concept. So you can get an idea of these three-dimensional concepts in the sense that if you have, look at this one, if you have, this is the three-dimensional concept, this is your xy plane. Okay, consider this yellow pen to be the z axis. Okay, then, and your particular point is here. At this point you have the particle. Then draw a line from this to this one, and whatever angle this is making, this is your theta angle. Okay. Then from this point where your particle is present, drop a perpendicular here on in this plane. This is your xy plane. So this xy plane, suppose this is your x axis, then whatever angle this will make with the x axis is phi angle. So if you look at this one, if it is making 0 angle at x axis, then it could go here, 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 and after 2 pi rotation it will come back to x axis. So the phi angle can rotate in the xy plane from x is equal to 0, from phi is equal to 0 to phi is equal to 2 pi. And if you are talking about theta angle, then this is your theta angle. So whatever angle this is making with the z axis is your theta angle. So this could be 90 here and this could be 180 here. So the theta is varying from 0 to 180 degree, and the phi is varying in the plane. So it is from 0 to 360 degree. So this is what is the coordinate system which we will be talking about. So if you look at this one, you look the same thing which I have written here, that your particle could be anywhere. So draw a line from origin to the particle, and it could be an infinite distance also, theoretically. Okay. So the distance between the origin and the particle is called position vector r, and it varies from 0 to infinity. Whatever this position vector is, whatever angle this position vector is making with the z axis is called theta. And then I said you, if the line is along the exactly the particle is on the z axis, then what is the angle theta which it will make with the z axis? It will be 0. If the particle is on the y axis, then what is the angle with which this line will make with angle with the z axis? It will be 90 degree. And if it is along the minus z axis, then this line will make an angle of 180 degree. So the theta can vary from 0 to pi. Okay, and your phi could vary from 0 to 2 pi, because it is the angle in the xyz plane, xy plane, and whatever angle it is making, if you drop a perpendicular from the particle in the xy plane and then you draw that point with the origin, whatever this projection is making an angle with the x axis is called phi angle. Okay, so phi is an angle in the xy plane, so it is from 0 to 2 pi. So the range of r is 0 to infinity, the range of theta is 0 to pi, and the range of phi is 0 to 2 pi. Okay. Now this, and x, y, z are the coordinate for Cartesian coordinate, in which we have written the Schrodinger wave equation 8 pi square m divided by h square e minus v psi is equal to 0. But okay, so it is like this one. If you look at this one, then here also from the north pole to the south pole is the positive and negative z axis. From the center of the earth, if you go to the north pole, it is your positive z axis. From the center of the earth, if you go to the south pole, it is negative z axis. And here you see this you have one axis here in this line, say x axis, another in the y axis. So what happens? You look at this point, if you go from here to here, if you go in this direction, the angle goes on increasing. Sorry. This angle, see 10, 20, 30, 40, 40 and so on. So it goes on increasing, and if you make a one complete circle, it will be 2 pi angle. So this latitude at 0 degree angle, starting from one point, if it makes a full one complete circle in this globe, then it covers 2 pi angle. So this angle is called your phi angle, and whatever be the angle between this a projection here and z axis is called the theta angle. Okay, just to give you an idea of the spherical polar coordinates. Now, if you relate this quantity r, theta and phi, and if you do some trigonometry, then what you find out is that z comes out to be equal to r cos theta, and x comes out to be r sin theta cos phi, and y comes out to be r sin theta sin phi. How does it comes? We will see. Okay. So if you look at this picture, then you see OZ and PM is parallel to each other. Okay, and with this line OZ and PM is since they are parallel to each other, we denote this with PM is equal to OZ is equal to Z. Okay, because it is along the Z axis. Now see, angle ZOP is the actually theta angle. Angle ZOP, ZO and P is the theta angle. So naturally OPM will also be theta, because this is the perpendicular which you drop from the P to the M on the xy plane. This dotted line tells you that it is a perpendicular. It is a perpendicular dropped from this point P to M, and M is a point in the xy plane. It is not below the plane. It is a two-dimensional image. It appears that it is below the plane. It is not below the plane. It is in the xy plane. Okay. So the angle OP and M and angle ZOP is equal to theta. Okay, no issue. Then PM, the same thing. PM is perpendicular to xy plane. Hence OMP is the angle pi divided by 2. Obviously, it is perpendicular to in the xy plane. So this angle is pi divided by 2. This angle is pi divided by 2. Okay. So for the right angle triangle POM, what you can write? Cos theta is equal to PM divided by OP. Cos theta is equal to, this is your theta angle. So cos theta is equal to PM divided by OP. So Z divided by R, and what does it mean? It means Z is equal to R cos theta. Z is equal to R cos theta. Same treatment with the other angles, right angle triangles, you get Y is equal to R sin theta sin phi and X is equal to R sin theta cos phi. So here what we did with these angles, with this relationship, this is X, Y, Z is the Cartesian coordinates, and R, theta and phi we are using in every case. Theta is here in every case, and phi is in the Y and X equation. Okay, sin theta sin phi and sin theta cos phi. So these three are the coordinates of spherical polar coordinates. Now we have a relationship between Cartesian coordinates and spherical polar coordinates. Once you have this relationship, then what you can do is that you can convert Laplacian operator del square psi by del x square plus del square psi by del y square plus del square psi by del z square into r, theta and phi equations. Okay, and then rest of the thing will remain same in the equation. Another important thing is that we have been using in case of Cartesian coordinate a relationship like this one, psi star psi d tau is equal to 1. Then we have used psi m, psi n, d tau is equal to 0, orthogonal condition and normalization condition. So, what do you use here in both the case is d tau, which is called volume element, and in Cartesian coordinate this volume element is actually dx dy into dz. Okay, infinitesimally a small cubical box, you can say, or a 3-dimensional box. Okay, not if it is not cubical. So, this was your volume element in spherical polar coordinates, in Cartesian coordinates. What will be the volume element in case of spherical polar coordinates? This is also important, because if you have to do the integral, then you need to know what kind of volume element you will take in place of d tau in case of spherical polar coordinates. So, the volume element is shown as the yellow region. This is your dV volume element. Okay, where we use dr is a small distance, a small part of the r coordinates. Okay, then this red line is r d theta and this green line is r sin theta d phi. So, if you multiply these three-dimensional volume element, so one is dr, another is r d theta, and third one is r sin theta d phi, and if you multiply these, then you get r square sin theta dr d theta d phi. So, this is your volume element, r square sin theta dr d theta d phi is the volume element. You see, I have multiplied dr, which is this blue shown by blue, then r sin theta d phi, which is shown by green, and then r d theta, which is shown by red. So, if you multiply these three, same way you multiply dx dy dz, here we are multiplying dr, r sin theta d phi and r d theta, and you are getting r sin theta dr d theta d phi as the volume element. So, instead, whenever we will treat our problem with the spherical polar coordinates, and if you require a volume element, then you will use this equation r square sin theta dr d theta d phi. Okay. So, what will be the now once you have this equation, z is equal to r cos theta, y is equal to r sin theta sin phi, and x is equal to r sin theta cos phi, then what you can do is you can convert Schrodinger wave equation into a spherical polar coordinates using these three equations. We will not do in the details, but in every quantum chemistry book, this kind of calculation you will find given in the appendix part. Okay, and it is not much needed also, but you will have to remember the form of the Schrodinger wave equation. So, this is your Schrodinger wave equation, h psi is equal to E psi, where h is the Hamiltonian, and you know this minus will not be there. Okay, this minus will not make it positive, minus h cross square divided by 2m del square plus v. Okay, and then you have del square is equal to this one. Del square is Laplacian operator. So, what we do is this Laplacian operator, when converted to a spherical polar coordinates using those three equations, z is equal to r cos theta and x is equal to what, y is equal to what, using those equations, what you get is this one. Del square is 1 by r square del by del r square del by del r, plus 1 by r square sin theta del by del theta sin theta del by del theta, plus 1 by r square sin square theta del square by del phi square. This is an equation which you will have to remember. Same way as you remember Schrodinger wave equation, that del square psi plus 8 pi square m by h square e minus v psi is equal to 0 is the most fundamental equation of quantum mechanics. Same way you will have to remember this equation also, that in case of spherical polar coordinates, the Schrodinger wave equation is 1 by r square del by del r square del psi by del r, plus 1 by r square sin theta del by del theta sin theta del psi by del theta, plus 1 by r square sin square theta del square psi by del phi square, plus 8 pi square m by h square e minus v psi is equal to 0. So, this the first equation we will have to remember, or because every time you are not going to derive that equation using those relationship of Cartesian coordinates x, y, z and polar coordinates r, theta, phi, which I have shown you in the earlier slides. Okay. So, this is the most fundamental equation, exactly in the same way as you remember the Schrodinger wave equation of Cartesian coordinates. Okay. So, this part, if you look at the Cartesian coordinate, this part is actually has only one variable is r only. Okay. see the complexity, the first term is r only, no theta, no phi. In the second term, you have r and theta both variables are there, because here you have r value 1 by r square and then you have theta, theta, theta everywhere. So, r and theta only, both. In the third part, you have all three presents, r is present, theta is present and phi is present. So, all three variables are there. So, the equation which you get, the Laplacian which you get is gradually, first term is r variable only, second term is r and theta variable, and the third term is all three variables r, theta and phi is present. Okay. So, using this Laplacian, you can write the Schrodinger wave equation which has a form like this one, 1 by r square. The only thing, this is the whole Laplacian. From this end up to this, you have the Laplacian operator. The only addition is psi. From the previous equation, the only addition is psi. Rest of the thing is same. Okay. So, you have 1 by r square del by del r square del psi by del r, plus 1 by r square sin theta del by del theta, sin theta del psi by del theta, plus 1 by r square sin square theta del square psi by del phi square. This was your, in case of Schrodinger wave equation, in spherical polar coordinate, this was del square psi. That's all. Okay. Plus rest of the thing remains same, 8 pi square m by h square e minus v psi is equal to 0. Now, if this is your Schrodinger wave equation, and if this Schrodinger wave equation you have to apply for the rigid rotor, then the first thing which you suppose is that rigid rotor is rotating in its plane freely without any force acting on it. And if that is so, then the potential energy will be 0. Okay. So, this part will become 0. Okay. And I have shown you from the classical rigid rotor concept that the moment of inertia I is equal to mu r square, okay. And for the sake of simplicity, we suppose that the line joining the two masses m1 and m2 is of unit length. So, length you take, r you take as 1, and if you take r as 1, then the equation reduces to this, all the first term where you have r only goes away, because you do not have r which is changing, r is 1. So, the first term goes away. In the second term also becomes a little easier, because 1 by r square sin theta. So, r square will become 1. So, it will be 1 by sin theta. Then del by del theta, sin theta, del psi by del theta will remain. Then again the third term, you do not have r, because r becomes equal to 1. So, it is 1 by sin square theta, del square psi by del phi square. And then we can write 8 pi square I divided by h square e psi, because again if you take r is equal to 1, then I becomes equal to mu, and mu is reduced mass. I said you, whenever you have a two body problem and you want to convert it into one body problem, then instead of mass you use reduced mass. So, you could have written 8 pi square mu by h square, and since it is a two body problem, we are converting to one body problem. So, instead of mass we use this mass, you use mu, and this mu becomes equal to I, because I is equal to mu r square and r is equal to 1. Okay. So, the equation which we have to solve for rigid rotor is this only, a very reduced equation, a simple equation, and with the assumption that the rotation is free, it is a freely rotating body. And the second assumption is that we do not have the length r varying in a haphazard manner, rather I have fixed the r to be equal to 1. And if r is equal to 1 and it is a fixed quantity, then this first term, the r equation of the Schrodinger wave equation goes. The second term becomes a little more simple. The third term also becomes simple, and the fourth term becomes even more simpler, because now you have 8 pi square I by h square e psi is equal to 0. But even then, in this particular equation, you have two different variables, theta and phi. Okay. So, these two variables are present here in this case, and they are representing the rotational and precessional motion of the system. Okay. So, whenever we have more than one variable in Schrodinger wave equation, what we do? We earlier did it for a particle in a 3-dimensional box. for particularly a two-dimensional box also, we do the separation of variables. So we will separate these variables and we will get independent equations so that we can solve those independent equations. The basic premise of this separation of variable is that whenever you have a wave function which depends on more than one variable, then you split this wave function into component wave functions, and the total wave function is the product of component wave functions. And when for such system, if the energy is also can also be splitted into component energies, and the total energy is the sum of the component energy. So this premise will always be used whenever you have to do the separation of variables. So then in the next module we will talk about the separation of variables and getting the separate equations for these two variables. Okay, and then we will try to solve those separate equations. One equation will be theta dependent, another equation will be phi dependent. For that, we take a break and we will come back in the next schedule with and we will start with the separation of variables. Thank you.